Across the unfathomable expanse of the small Magellanic Cloud, a satellite galaxy tethered by gravity to our own Milky Way, floats an object of profound and unsettling contradiction. From a distance of nearly 200,000 light-years, it appears as a single, unremarkable point of ruddy light, catalogued and filed among millions of its stellar brethren. It is a supergiant star, a bloated, luminous body designated HV 2112, swollen to a diameter so vast that were it to replace our own Sun, its tenuous outer atmosphere would engulf the orbit of Jupiter. Its surface temperature is a relatively cool 3000 Kelvin, giving it the characteristic crimson hue of an aging star in the twilight of its existence. Yet, within this seemingly conventional stellar titan, an observation of its spectral signature reveals a chemical composition so anomalous, so radically divergent from the established pathways of stellar nucleosynthesis, that it forces a re-evaluation of the very life cycles of the most massive stars. Its light speaks of an impossible alchemy, a forge operating under conditions that should not exist within the core of a star of its class. The presence of exceptionally high abundances of heavy elements like lithium, molybdenum, and rubidium points not to the slow, steady fusion of a conventional star, but to an engine of immense violence and exotic physics, hidden deep beneath the roiling, convective clouds of its visible surface. This star, in its quiet, distant glow, presents a paradox. It shines with the light of a known stellar type, but it breathes an atmosphere laced with the byproducts of a process that should have destroyed it. It is a star that shouldn't exist, a placid facade concealing a dark and compact secret, an object of unimaginable density spiraling within its heart, rewriting the laws of its own evolution from the inside out. Long before this stellar hybrid was formed, in an era of the galaxy's history far deeper than human record, the space now occupied by this single object was home to two. They were a binary pair, gravitationally bound in a slow, majestic waltz that had persisted for millions of years since their birth from the same turbulent nebula of primordial gas and dust. The primary star of this duo was a colossal specimen, perhaps 25 times the mass of our Sun, a brilliant blue-white titan burning through its hydrogen fuel with ferocious intensity. Its companion was a smaller, though still substantial star, a body of around 5 solar masses, destined for a much longer, less dramatic life. For eons, they orbited their common center of mass, their immense gravities warping the fabric of spacetime around them, their stellar winds intertwining in intricate, glowing shockwaves of charged particles. The primary star, due to its immense mass, lived a life both brilliant and brief. Its core was a crucible of fusion, transmuting hydrogen into helium at a prodigious rate, the outward pressure of this thermonuclear furnace holding the crushing force of its own gravity at bay. The smaller companion followed a more sedate evolutionary track, its own internal clock ticking at a much slower, more deliberate pace. An observer in that distant time would have seen nothing to suggest the extraordinary future awaiting this system. It was one of countless massive binary pairs scattered throughout the galaxy, their fates seemingly preordained by the fundamental principles of stellar physics. The larger star would exhaust its fuel, swell into a supergiant, and detonate in a core collapse supernova, leaving behind a compact remnant, while the smaller star would continue its own journey toward a more placid end. The intricate dance of their orbits, the steady emission of their light, the silent, patient operation of gravity, all pointed toward a conventional, albeit spectacular, conclusion. Yet, the precise parameters of their separation and their respective masses contained the latent potential for a far stranger outcome, a confluence of events that would depend on the timing of one star's death and the other's subsequent evolution, setting the stage for a merger not of two living stars, but of a living star and the ghost of its long-dead companion. The end for the primary star came not with a whimper, but with a cataclysm of unimaginable scale. After burning through the hydrogen in its core, it began to fuse helium into carbon and oxygen, then carbon into heavier elements, climbing the periodic table in a desperate, layered battle against its own immense gravity. Each successive stage of fusion provided less energy and lasted for a shorter duration, the star's internal structure growing to resemble an onion, with a dense core of iron and nickel at its center, surrounded by shells of silicon, oxygen, neon, carbon, helium, and an outermost envelope of hydrogen. Iron, however, marks the end of the line for stellar fusion. Its nucleus is so tightly bound that fusing it into heavier elements consumes energy rather than releasing it. The furnace at the star's heart was extinguished. In a fraction of a second, the outward thermal pressure vanished, and the delicate equilibrium that had supported the star for millions of years was shattered. Gravity, relentless and unopposed, won the final battle. The iron core, with a mass greater than our Sun packed into a volume smaller than the Earth, collapsed in upon itself. Electrons and protons were crushed together in a process of inverse beta decay, forming a sea of neutrons and releasing a stupendous burst of neutrinos. The collapse was so violent that the core rebounded, slamming into the still infalling outer layers of the star and creating a shockwave of monumental power. This shockwave, energized by the torrent of neutrinos, blasted outward through the star's layers, tearing the colossal body apart in the brilliant, ferocious explosion of a Type II supernova. For a few weeks, the dying star outshone its entire host galaxy, seeding the surrounding interstellar medium with the heavy elements forged in its life and its death. But left behind at the heart of the expanding, incandescent nebula was the collapsed core, a neutron star. It was an object of physics taken to its extreme, a sphere perhaps only 20 kilometers in diameter, yet containing the mass of 1.5 suns. Its matter was so dense that a single teaspoonful would weigh billions of tons, its atoms crushed out of existence, leaving only a bizarre fluid of tightly packed neutrons held up not by thermal pressure, but by a quantum mechanical principle known as neutron degeneracy pressure. This stellar corpse, this dark, compact remnant of a once mighty star, continued its silent orbit, a gravitational phantom now circling its still living, and entirely unsuspecting, companion. The supernova that birthed the neutron star was not a gentle event, it was an asymmetrical explosion that imparted a kick to the compact remnant, altering its orbit around the surviving companion star. For a time, the system found a new, albeit altered, equilibrium. The neutron star, a tiny point of immense gravity, circled the larger, now solitary star, a silent testament to the violent death of its former partner. But the surviving star's own evolutionary clock had not stopped. As it exhausted the hydrogen fuel in its core, it too began to change, its own structure shifting to accommodate the onset of helium fusion. Its outer layers, no longer held as tightly by the star's gravity, began to expand, cool, and glow with a deep, crimson light. It was entering its red supergiant phase. This expansion was not a minor adjustment, it was a transformation of colossal proportions. The star's radius swelled by a factor of hundreds, its photosphere bloating outward across millions of kilometers of space. Inevitably, the expanding atmosphere of the red supergiant reached the orbit of the neutron star. The compact object, once orbiting in the vacuum of space, now found itself moving through the tenuous, but still substantial, outer plasma of its companion. This was the beginning of the common envelope phase, a critical and inherently unstable period in the life of the binary system. The neutron star, with its powerful gravitational field, began to plow through the supergiant's gaseous envelope, creating a drag force of immense magnitude. This friction acted as a brake, causing the neutron star to lose orbital energy and momentum. It could no longer maintain its stable, distant orbit. Instead, it began a slow, inexorable process of spiraling inward, deeper and deeper into the fiery heart of the red supergiant. The common envelope itself became a site of tremendous energy release, as the orbital energy lost by the neutron star was converted into heat, causing the shared atmosphere to glow more brightly and, in many cases, to be ejected into space. For the system of HV 2112, however, the envelope was not fully cast off. Instead, the red supergiant was massive enough, and the neutron star's spiral slow enough, that the two objects were destined for a far more intimate and transformative encounter, a collision course set not in open space, but within the very body of a living star. Within this swirling, incandescent prison of hydrogen and helium plasma, the neutron star began a slow, inexorable descent toward the supergiant's core. Its journey was not a simple plunge, but a protracted spiral decay lasting thousands of years, a cosmic whirlpool of unimaginable scale and violence. As the neutron star moved through the increasingly dense layers of the supergiant's envelope, the frictional drag intensified exponentially. It carved a tunnel through the stellar material, generating a powerful bow shock ahead of it and leaving a turbulent, superheated wake behind it. The energy dissipated by this process was immense, equivalent to thousands of times the total output of our Sun, all of it released deep within the supergiant's interior. This injection of energy fundamentally altered the star's internal structure. It drove powerful, chaotic convection currents, disrupting the orderly flow of energy from the core to the surface. The entire star would have trembled, its luminosity fluctuating as these internal shock waves and heat blooms propagated outward. For an outside observer, the supergiant would have appeared unstable, its brightness varying erratically, its surface roiled by disturbances far more violent than normal stellar convection. The neutron star itself became an engine of accretion. Its intense gravitational field captured a fraction of the surrounding plasma, pulling it into a swirling, superheated accretion disk around its tiny, 20-kilometer form. As this material spiraled inward toward the neutron star's surface, it was compressed and heated to millions of degrees, releasing intense bursts of X-rays and high-energy particles. This accretion process, however, was throttled by the sheer density of the surrounding medium. The neutron star was moving too quickly and the gas was too thick for a stable, continuous disk to form. Instead, the interaction was a messy, violent affair, a continuous churning of the supergiant substance by a gravitational anchor of near-absolute density. The journey inward was a process of mutual destruction and transformation. The neutron star's orbit decayed, bringing it closer to its fate, while the supergiant's envelope was superheated, churned, and partially stripped away, its own evolutionary path irrevocably diverted by the intruder burrowing toward its heart. The long, slow spiral culminated in the moment the neutron star finally reached the central region of the red supergiant. Here, it encountered the supergiant's own native core, a dense sphere of helium, or perhaps carbon and oxygen, where the star's own thermonuclear fusion was taking place. The collision was not an instantaneous impact in the conventional sense, but a rapid and catastrophic disruption. The neutron star, being vastly denser than the supergiant's core material, did not bounce off or merge cleanly. It plunged directly through it. The immense tidal forces exerted by the neutron star shredded the supergiant's core, tearing it apart and scattering its material throughout the central cavity. The fusion processes that had powered the supergiant for millions of years were abruptly extinguished as the core's structure was obliterated. In the chaotic aftermath, a new equilibrium began to form. The scattered material of the supergiant's original core, along with the hydrogen and helium of the innermost envelope, was captured by the dominant gravitational field of the neutron star. This material settled into a thick, obscenely hot and dense accretion sphere around the compact object. The neutron star, the remnant of the system's first massive star, had now effectively replaced the original core of its companion. It had become the new center of gravity, the new engine at the heart of the bloated supergiant. This was the moment of birth for the Thorn-Zitko object. The star was now a hybrid, a fundamentally new type of celestial body. Its outward appearance remained that of a red supergiant, a vast, luminous, low-temperature sphere of gas. But its internal structure was alien. It was a star with a neutron star for a core, a star no longer supported by the outward pressure of nuclear fusion, but by a far more exotic and precarious mechanism. The transition would have been violent, likely causing the star to expel a significant portion of its mass in a powerful outburst, but when the dust settled, what remained was a stable, albeit temporary, configuration, a star that looked ordinary on the outside but was powered by a process that defied the standard models of stellar life. The newly formed Thorn-Zitko object operates on a principle fundamentally different from any normal star. In a main-sequence star like our Sun, or even in a conventional red supergiant, the energy that prevents gravitational collapse is generated by thermonuclear fusion in the core, hydrogen to helium, helium to carbon, and so on. The star is a self-regulating fusion reactor. The TO, however, lacks a conventional fusing core. Its engine is the neutron star itself, and its fuel is the very substance of the supergiant envelope that surrounds it. The immense weight of the star's outer layers presses down on the central region, and this material slowly but continuously accretes, or falls, onto the surface of the embedded neutron star. As this gas falls through the neutron star's extraordinarily steep gravitational well, its gravitational potential energy is converted into kinetic energy, and then, upon impact with the neutron star's surface or the dense accretion sphere around it, into thermal energy. The heat generated by this continuous, controlled gravitational collapse is immense, producing a luminosity that rivals or even exceeds that of a normal supergiant. This process is what holds the star up. The intense radiation pressure from the superheated accretion zone pushes outward, supporting the weight of the overlying envelope and preventing the entire star from collapsing onto the neutron star core. The entire structure exists in a delicate, self-regulating balance governed by a concept known as the Eddington limit, the maximum luminosity a star can have before its own radiation pressure becomes so strong that it blows its outer layers off into space. The TO naturally throttles its own accretion rate to hover near this limit. If too much material falls onto the neutron star, the resulting energy release increases, the outward radiation pressure intensifies, and it pushes the surrounding gas away, temporarily slowing down the accretion. If too little material falls, the luminosity drops, the radiation pressure weakens, and gravity pulls more material inward, reigniting the process. It is a star powered not by the fusion of elements, but by the relentless, throttled force of gravity itself, a continuous, slow-motion implosion radiating energy outward to create the illusion of a stable, living star. It is this unique central engine that provides the solution to the chemical mystery observed in the spectrum of HV 2112. A normal red supergiant's convection currents are not typically hot or deep enough to dredge up unusual elements from the core to the surface, and its own fusion processes do not produce the specific combination of heavy elements seen in this object. The Thorne-Zitko object, however, provides an entirely different environment for nucleosynthesis. The surface of the accreting neutron star core is one of the most extreme physical locations in the universe. The temperature is in the billions of Kelvin, and the density is immense. As the hydrogen and helium-rich material from the supergiant's envelope rains down onto this surface, it is subjected to conditions that trigger a host of exotic and rapid nuclear reactions. This is not the slow, steady fusion of a normal stellar core. Instead, it is a violent, explosive process known as the rapid proton process, or RP process. In this environment, atomic nuclei are bombarded with a furious flux of protons. They capture these protons one after another, rapidly building up to form heavier and heavier elements before they have a chance to decay radioactively. This process can forge elements far beyond iron, creating isotopes of rubidium, strontium, yttrium, zirconium, and molybdenum, elements that are exceptionally rare in normal stellar atmospheres. Furthermore, the conditions are also perfect for the synthesis of lithium, an element that is typically destroyed in the hot interiors of most stars. Once these exotic elements are forged on the surface of the neutron star, they do not remain trapped at the core. The TO's entire structure is dominated by powerful, large-scale convection cells, driven by the intense energy release from the central accretion zone. These currents, far more vigorous than in a normal supergiant, act as a massive conveyor belt, dredging the newly synthesized material up from the deep interior and carrying it all the way to the star's visible surface, the photosphere. There, these elements become imprinted on the star's outbound light as unique absorption lines in its spectrum, a telltale chemical signature that betrays the presence of the impossible engine burning deep within. The anomalous chemistry of HV 2112 is not an anomaly at all. It is the broadcast signal of a Thorne-Zitko object, the chemical echo of a neutron star consuming its companion from the inside. Like all massive stellar objects, the Thorne-Zitko object is a transient phase, a temporary balancing act against the inexorable force of gravity. Its lifespan is limited by the amount of fuel available in its vast envelope, a supply that, while enormous, is finite. The star's ultimate fate can follow one of several dramatic and divergent paths, each one dictated by the precise mass of the neutron star core and the rate at which it accretes material from the surrounding envelope. One possibility is a relatively quiet demise. Over a period of perhaps 100,000 to 1,000,000 years, the TO will consume or blow away its hydrogen envelope through its intense luminosity and stellar winds. As the envelope thins, the accretion onto the core will dwindle, and the star's luminosity will fade. Eventually, the envelope will be completely stripped away, revealing the bare neutron star at its heart. This object, however, would be unlike the neutron star that first entered the supergiant. Having accreted vast quantities of mass and angular momentum from the swirling envelope, it would likely be a rapidly spinning pulsar, a millisecond pulsar, surrounded by a faint, expanding nebula of the supergiant's last remnants. The hybrid star would be gone, leaving behind a hypercaffeinated stellar corpse, beaming radiation across the galaxy as it spins hundreds of times per second. A more spectacular end, however, awaits if the accretion process is too efficient. A neutron star cannot grow indefinitely. There is a theoretical upper mass limit, known as the Tolman-Oppenheimer-Volkoff limit, estimated to be between 2 and 3 solar masses. If the accretion of material from the supergiant's envelope pushes the neutron star's core beyond this critical threshold, neutron degeneracy pressure will no longer be sufficient to counteract the crushing force of gravity. The core will undergo a second, catastrophic collapse. This time, there is nothing to halt it. The neutron star will implode in a fraction of a second, forming a stellar mass black hole at the very center of the Thorne-Zitko object. The sudden disappearance of the core and the formation of an event horizon would trigger a unique and bizarre type of supernova. The inner layers of the supergiant envelope, suddenly losing their central support, would begin to fall inward toward the new black hole, forming a massive, superheated accretion disk that would launch powerful relativistic jets, blowing the star apart from the inside. The result would be a black hole-induced supernova, a final, brilliant explosion that would obliterate the star and announce the birth of a new black hole to the cosmos. The existence of such an object, even if only as a transient phase in the life of a rare binary system, has profound implications for our understanding of the cosmic ecosystem. The universe is not just a place of predictable, linear evolution, it is a laboratory where gravity can force matter into the most extraordinary and unexpected configurations. Thorne-Zitko objects represent a hidden pathway in stellar evolution, a channel through which the universe can create unique chemical signatures and potentially new types of stellar remnants. The exotic nucleosynthesis occurring at their cores contributes to the chemical enrichment of the interstellar medium in a distinct way. When a TO ends its life, whether by slowly shedding its envelope or by exploding in a final cataclysm, it seeds the surrounding space with the peculiar elements it has forged. The lithium, molybdenum, and other heavy elements created by the RP process are cast out into the galaxy, where they will eventually be incorporated into new generations of stars and planets. A small but significant fraction of the heavy elements found in our own solar system, in the Earth, and even within our own bodies, may have been created not in the heart of a conventional star or a standard supernova, but on the superheated surface of a neutron star buried deep inside a stellar hybrid. These objects, therefore, are not mere cosmic curiosities, they are participants in the great cycle of galactic alchemy. They demonstrate that the interplay of binary stars can lead to outcomes far more complex than a simple orbiting pair. The merger of a living star with the corpse of another creates a system that is greater, and stranger, than the sum of its parts. It is a testament to the fact that even in death, a star can have a second, profoundly influential life, acting as the engine for its companion and fundamentally altering its destiny. The single, unassuming point of light in the small Magellanic Cloud is a reminder that the most revolutionary discoveries are often hidden in plain sight, their secrets encoded in the subtle language of light, waiting for us to decipher the story of a star that consumed a star, and in doing so, became something entirely new, a fleeting but brilliant ghost in the cosmic machine. The quiet glow of HV 2112 is not just the light of a distant sun, it is an echo of a violent merger, a beacon powered by gravitational collapse, and a chemical fingerprint of one of the most exotic stellar objects ever conceived. It stands as a monument to the universe's capacity for complexity, a celestial paradox that bridges the gap between life and death in the grand, silent theater of the cosmos.